All right, guys, nice to meet you. And today I would like to talk about nonlinear Fokker Planck equations and its applications. So according to the uh, picture you can see on the screen, you can see density probability distribution. And according to the definition of this equation, Fokker Planck equation is a partial differential equation that describes the time evolution of the probability density function of the velocity of particle under the influence of direct forces and random forces, such as Brownian motion. Yeah. And we talk especially about non-linear Fokker Planck equations. Well, non-linear Fokker Planck equations have found applications in various fields, such as plasma physics, for example, plasma physics. It's very interesting how this works inside, right? Also, some examples about surface physics. Some examples we can find in this field. By the way, common used example is when we use this equation in physics of polymer fluids. Let's type it here. Okay, physics of polymer fluids, something like this. Yeah. So we need to describe how this particle of will move. The mean speed and direction according to the forces which influences particle and some noise. Okay, some Brownian. The motion is Brownian, so it is quite random, right? So particle beams is also common example. Particle beams, right? Oh, very interesting. Particle beams. For example, we have a laser, and this particle beams is going very quickly. And to describe this behavior, we can use Fokker Planck equation, but sometimes behavior can be nonlinear. So we want to talk about specifically about nonlinear Fokker Planck equations. And not so much time ago, these equations were about was used also in marketing field. So this bold guy said, I want to use Fokker Planck equation to describe probability density function of my system, blah blah blah, etc. And well, he even wrote a paper about this, and he wanted to use it in marketing field. By the way, some Chinese guys, you can say this, also wrote a paper about how they used Fokker Planck equation to estimate, calculate asset price fluctuations, and they say they can. This topic is very probably actual or interesting because real estate is very expensive, If you can predict the fluctuation, maybe you can get some profit or maybe not lose something because price is changing over time. And they draw some equations. So you can say we want to use Fokker Planck equations to this, to calculate this probability density function of asset price fluctuations. Yeah. Very interesting work, which is a little bit old. Was published maybe in 2004. Okay. We can use it not only in marketing, but also in some other different fields. I can show you more examples. So, for example, in hydrodynamics or non-linear hydrodynamics, non-linear hydrodynamics and dynamics. It's about hydrogen. Hydrodynamics about water, so fluids is changing over time. It can be used in a boat, or maybe fly when you fly. We also, but okay, maybe also about water, only about water. But when they fly, I want to eat something. And okay, yeah, this is a common example. So it's about hydrodynamics, but we can use nonlinear hydrodynamics. What is it about? How do you think? Behavior is quite nonlinear, should be. Okay. We can see more examples. However, I think we understood the some main principle. Okay. Maybe I will show you a few new interesting examples here. So let's see. Also, theory of electronic circuitry. Electronic circuitry is also used. Okay, not like this. I made a mistake. So circuitry. Yeah, this is quite more comprehensible. So, by the way, we can see some applications of nonlinear Fokker Planck equations, and it is very important. Maybe population dynamics. So they grow over time, and more people. And maybe we can use also for nonlinear Fokker Planck equations to predict this, to predict density of probability function. Yeah. Also in engineering, by physics, in some laser arrays, we can use this nonlinear Fokker Planck equations. Also, yeah, for people's population grow. So maybe we can use these equations also to, in a sense, more precise. Yeah, so in a sense, more precise. Okay, some human movement in science. It's more about medicine. Okay, and yeah, I will show you human movement science. Yeah, this exists in the world of real science. So we want to know how the humans move. We can also use some near blood equations or maybe some blood inside his body. Also, we can describe behavior of these fluids in the body like with Fokker Planck equations, nonlinear Fokker Planck equations. Okay, near physics, psychology, and marketing uh, also can use this equation. And in spite of the diversity of these research fields, many phenomena addressed therein have a fundamental physical mechanism in common. They arise due to cooperative interactions between the subsystems of many body systems. So we have many body systems and they interact with each other. And these cooperative interactions, result in reduction of larger number of degrees of freedom of many body systems, and in doing so, uh, bind subunits of many body systems by means of self-organization, of course, into synergetic entities. So these synergetic many body systems admit low-dimensional descriptions. See some more, maybe it will be more comprehensive if we will watch this picture, right? Because we see it by our eyes in the world. And yep, these energetic many-body systems admit low-dimensional descriptions in terms of nonlinear Fokker Planck equations that capture and cover the essential dynamics underlying the observed phenomena. So the phenomena that we address in this course range from equilibrium and non-equilibrium phase transition, and yeah, more pictures is interesting. What is equilibrium? It's like in the middle, yeah. Equilibrium phase transition. So please found some example. Come on. So equilibrium is like yeah, equilibrium in the middle, right? So we have non-equilibrium and non-equilibrium transition, and the multi-stability of systems, convergence of power law, and cutoff distributions. This power law distribution, I will show you. It is very real life distribution that we can see in the world. I saw this price. Yeah. So we can see the distribution in our real life. So usually we assume that we have normal distribution to some phenomena in the world. However, in real life, we have a power law distribution. That's what my professor told me. Okay. Also, we have distortion of Boltzmann distribution. And what is Boltzmann distribution? I will show you. Boltzmann distribution is also interesting. Looks like this. Quite similar. And we will study possible asymptotic behavior of systems such as approach to stationary distributions. Looks like stationary distributions. Okay, not like this, but let's say, okay, also the emergence of non-stationary traveling wave distributions, and maybe it's quite specific. However, let's see an example. Non-stationary traveling wave, wave distribution. Ah, looks like. Okay, maybe next time. What I want to say is, we will be concerned with the novel and anomalous diffusion, and it's quite important because Fokker equations include inside some coefficients to describe behavior. It's called diffusion term, and it'll be interesting to know how this diffusion and some how can we see some anomalies diffusion. Yeah, so we have some diffusion, some particles go to another particles, and then like this. Quite anomalous distribution. Very interesting article. Objective comparison of methods to decode anomalous diffusion, which was published in Nature some time ago. So there's cells and there can be some diffusion and it can be anomalous. Yeah, we can save this article. I think some algorithm to generate some trajectory. Very interesting. Maybe we can use it in our own research. Yeah. Steal this article to our folder. This is our article review. So, our review of Fokker Planck equations step by step. So, we concerned with normal and anomalous diffusion, and we will examine how correlation functions evolve with time and in these kinds of synergetic systems. And by the way, you will ask me what is correlation function? Okay, I will tell you. Correlation function. Maybe we have to see correct definition. What's that look like? Okay. Maybe next time. Now we want to see the picture in general. So we want to discuss about the Planck approach. And usually people are, or some scientific scientists around the world use this approach in quantum statistics, in the near non-equilibrium thermodynamics, and in generalized extensive and non-extensive thermostatistics. Our goal in this course is to provide an introduction to the theory of nonlinear Fokker Planck equations and to highlight what systems described by nonlinear Fokker Planck equations have in common. So this is full of examples where we can see where we can see nonlinear Fokker Planck equations can be used. And yeah, maybe one example, as I said before, quantum statistics is quite a little bit complex. Let's see, what is it about? Quantum physics, quantum statistics statistics. Yeah, because there are also some particles. They move around, right? Very interesting. By the way, we have also linear non-equilibrium thermodynamics. That's here, linear non where's my pen? Equilibrium dynamics. No. It's in real life. It looks like the locations. Let's see its articles. What is it inside? We respect this journal, MDPI. Oh, I think that we attack this website. Really, I have so much questions, and sometimes Google thinks that I'm a robot. I'm a scientist. I want to say. So, theoretical considerations and concepts we will illustrate by various examples and applications. As we can see here, a lot of examples. Fokker Planck equations can be used, nonlinear Fokker Planck equations. And specifically, this article is quite also interesting. Let's open it. Okay, let's see, it should be found here. Let's watch this article. Okay, non-equilibrium thermodynamics foundation of the origin of life. I think this is quite interesting article. Over the last 2,000 years, humanity has proposed very blah. Then four systems and planets. Yeah, very interesting. Yeah, I guess it's about entropy, no? Entropy. So entropy equals inside and outside. Okay, internal and external entropy. Blah blah blah. And okay, we have some bifurcation diagram here showing how for nonlinear non-equilibrium systems, two or more solutions suddenly appear at what is known as a bifurcation for a particular parameter lambda of the system, which may be, for example, the strength of the external force over the system. So which branch the system takes depends on microscopic fluctuations and positive feedback. Outer corresponds represent blah. So this is a little bit interesting because in probabilities selection through yeah, quite selection. This is changing our entropy, and this is another parameter. Yep, that is box. Oh, wait, thanks. I think we can save this article and maybe decide further in the future. Oh yeah. So this is a microbiology example, and here we can see some multiplication diagram, how it is applied to this process. And crystals grow in biochemistry, and this process is Fox. So I would like to save this article. It is very interesting. We can save further in the future. However, I want to sum up maybe a topic of our lesson. So, okay, maybe some statistics. This is interesting to see. This will be our last example. Really, non-extensive thermostatic. Let's see. Why? Expensive. Okay. Maybe next time. Common and like this. So, due to the ramification of the theory of nonlinear Fokker Planck equations in various scientific fields, this course is designed for people who like to see how the behavior of self-organized systems that may be more complex than even our human body. So you can see how you or me is moving inside these complex systems, these self-organized systems. It can be social complex systems, for example. Okay, so this course designed for maybe some researchers and which is also can be interested in biology, in neurophysics, in some researches in human movement sciences and psychology, and etc. And I hope that this course will make audience interested in this topic of nonlinear Fokker Planck equations, and researchers will see the connections between these different areas in which nonlinear Fokker Planck equations have been applied in business, in social science, in chemistry, in plasma physics, in physics of polymer fluids, and yeah, it's in some sciences like human movement science and etc. So thank you very much for your attention, and I hope that with this course of complex systems will be helpful for you, and you will apply these ideas for different areas. Maybe you can implement some algorithm to solve some complex problem, and we will also show some mathematical formulas. But the first one, the first thing we have to see common general ideas that are behind this formulations. Sorry for my yeah. And that's it. Thank you very much, and bye bye.